All right, so today we're going to talk about debugging, and I'm going to give you a tutorial on GDB, which is GNU's debugger. It's a text user interface debugger that you'll be using next week in your hack to debug a tic-tac-toe program. I've got a bad program in the background that we're going to be able to play around with. But before we do that, let's motivate why we want to use an actual real debugger, okay? Using printf statements is a poor man's, it's sometimes referred to as poor man's debugging. I should have made sure that the live stream is good. Yeah, we're good. All right, so using printf statements is a poor man's way of debugging because using the standard error output is error prone and brittle. Remember that undefined behavior is undefined behavior. You could have like 10 lines of code, like code 1 and then you print something, code 2 and then you print something, code 3 and then you print something. And what could happen is that the error could occur down here on line 8, but it'll make it look like it's occurred on line 2 because the stuff that you wanted to print in between those two things is stuck in a buffer, the output buffer. We all know what buffers are. If you ever try to watch a video online and you've got a slow connection, right, it starts buffering, right, because you need to download some more data before it'll actually display the next 10 seconds or something. And so the output is like that, exactly like that. It gets saved to a file, an output buffer. I don't want to call it file yet because we're not there. But it gets saved to an output buffer, and it only gets flushed out to the screen when it feels like it's necessary, because that's an extremely expensive operation. So if it feels like it's not worth it to do, then it won't do it unless you force it to flush out to the output. Again, standard output and standard input, by the way, is a buffer, and it may not give the correct impression on where the bug is. Right? You could print out OK to line 42, but the error actually occurred on line 52 because you never actually see any of that output. You constantly have to add new print statements, and okay, I fixed that bug. Now I need to delete that. Add back. Oh no, now something else is broken. I need to add all those statements back in. It's a lot of work for not a lot of payoff. Right? Instead, what you'll want to do is you'll want to use a proper debugger. A debugger is simply just another program that runs or simulates your program, right, on a particular input, or you can control those inputs actually, and you can pause the program. You can take a look around, right? What value does that variable have at this point in the program? What value does that have at this point in the program? You can also, I shouldn't call it walk. You can step through a program line by line because that's the actual command that we'll use, step, right? And the debugger that we're going to be using is GNU's debugger, right? GDB stands for GNU's debugger, right? And that's what it's called, right? There is a nice little cheat sheet here. If you want to go ahead and take a look at that URL, that'll be available in the notes. That's going to have a cheat sheet that you can print out with all the common commands that you would use with GDB, right? So what I want to do is I want to start using it. We'll just get into it and we'll do an actual tutorial here. Just like I demonstrated on Monday and you did in your lab on Tuesday, when you use a dynamic analysis tool like Valgrind or now GDB, you need to use that G flag, that -G flag. If you don't use it, we saw on Monday that we're not able to tell where that seg fault happened on line 52 or line 42 or whatever, right? Because the line numbers were gone at that point. The G flag preserves those line numbers so that we can diagnose the problem further, right? Like I said, it's not a graphical user interface. It's a text user interface, a TUI, right? To run it, to get it started, you simply just invoke GDB and then whatever your program's name is. Right? In this case, a.out. Let me show you. All right, so I've got an array program here. It's pretty buggy. Yeah, go ahead. The GDB, and then a.out. Right? So I've got a buggy program here. Let's find out what it's supposed to do first. What I do is I create, n is 77 here. Actually, I think that was supposed to be 7. No, I'll leave that there. That's an intentional bug. But I create an array here of size 7. Right? Obviously, that's wrong. and I set it equal to the first 7 primes, 2, 3, 5, 7, 11, 13, and 17. Right? Then I pass this off to the sum function, right, which is supposed to add them up. It simply iterates over this the number, and then it adds them all together and then returns the result. So what is the sum of the first 7 primes? I don't know, Wolfram Alpha, you tell us. Sum of first 7 primes. Right. There's my expected output, 58. Okay. When I compile this though, GCC array boogie, right? There, okay, clear that. Ignore that for now. Right, I'm going to shut off all the warnings. Right. There are some things that GCC will catch as a static analysis tool. I'm just going to go ahead and run it. It was and segmentation fault. Where did it happen? I have no idea from just this output. So I could run valgrind and I could get a report back that says it occurred on line 52 or whatever. But I'm going to go ahead and fire up GDB instead because it's way more interactive. GDB a.out. I'm now running GDB, right? Not that satisfying. It's just a command prompt, right? This is another program that I can give commands to, right? So the first thing I'm going to do is I'm going to go ahead and go at layout next, right? And it displays my code to me. Now, is that my code? Is that my C code? No. What is that? That's machine code. Actually, I think that's the assembly code, right? I can go layout next, and there, layout next, right? There it shows them side by side, but we're not actually running the program next. Next. There we go. Layout next. No, layout next. Something happened here. Did I not? Oh, sorry. Yes, that's why it was not available. What did I need to compile with? The G flag, right? I was overzealous here with the W flag, and I forgot all about the G flag. Right? So let me just go ahead and jump immediately to the source. Layout SRC. SRC is short for source. And it'll show me my source code here. Of course, I can always look at it up above, but this shows me my source code as I'm executing this program. Let me go ahead and run the program with just as it is. Right? There, we got a seg fault, a segmentation fault. Now does it tell you what line it is at? Right there, 17. In fact, it's highlighting that line up above right here. Right? There was something wrong immediately with that. Okay? So I want to diagnose what went wrong. I want to walk through this program line by line. So what I'm going to do is I'm going to set a breakpoint at line, say, 13. Did you see the difference there? There's this B plus right here. That's a breakpoint. If I run the program, rerun the program, then it will stop at that line, right? So run. Yes, I want to restart it. Right? So there you go. Now we're at this line right here. The capital B and then the arrow key means that, or the arrow, the Langle-Wrangle thing there is telling me that I'm at this current line. Now I can step through this program line by by going to the next line. Right? That's set n equal to 77. In fact, I can even print that. What value does n have right now? 77. Right? What value does primes have? Primes. Right? Some random value, garbage value. Why? Because we have not executed line 16 yet. Right? So let's go ahead and go next. And in fact, it's such a common thing to do with next that you only have to go n. Right? N to go to the next line, next line, next line. Now let's print out primes. Right? Hey, 7? Does that sound like a valid memory address to you? No. And 77, that's wrong too, right? Already, I'm just by slowing everything down and looking at it line by line, I've already discovered 2 bugs here. So I'm going to get rid of the debugger by quitting out of it. Yes, I do want to quit. Right? And now I can come back up here and realize 2 of my mistakes. My first mistake here is that n is supposed to be the size of the array. If you're trying to sum the first 7 primes, should it be 77? Nope, should be 7. Right? My second bug here is, should I be setting a pointer variable to a 7? Right? Does that memory location exist? Maybe. Does it belong to me? Almost certainly not. I want this to be a dynamic array. So what should I do? Malloc it. Int star malloc size of n times n. Correct? Nope. But let's see. Let's diagnose it. All right. So GCC this, run it again, all right, and let's go ahead and run. It still errors out at line 17. Why? You can actually get values of your expression. So, for example, I'm staring at this thing right now, and I know that it's wrong. But let's go ahead and find out why it's wrong. If I print out n, 77. Oops. I thought I didn't I redo it? There we go. GDB a dot out. All right, there we go. Now run it. Still at line 17 there. So let's print out n. Why is it 77? That's right. Where am I? I'm in. Okay, which one are you that I'm editing? Okay, I was editing the wrong one. Sorry. That'll screw up another demonstration I'm going to do on Friday. So I'll have to go back and fix that. So there we go. Malloc. And again, I'm going to do the intentional error here of size of int, or size of n. It should be size of int. All right, there we go. GCC this. And let's run it again. If you just run it again, you'll... Oh, I actually got it to go without a seg fault there. But is that the actual value that I should be getting of the sum of the first 7 primes? No, it should be 58. I've got a bug here. Right? So let's go ahead and fire up GDB, a dot out. And I do want to set a breakpoint at line 16, layout SRC, right? So that we can check and see what's going on that particular line, because it is wrong. Run. All right, there we go. So we've run up to this line. Am I about to allocate correct memory? Let's print out n. Now we've got it at 7. That's correct. Print out size of n. Right? Oh, okay. We got away with it. Right? Why did we get away with it? And print size of int. There we go. 4 and 4. We got away with it. It just happened to be that one thing was equal to 4 and the other thing was equal to 4. Why is size of n giving me 4? What is n? An integer. How many bytes does an integer take? 4. Right? So, yes, it gave me the correct answer, but for the wrong reason. Right? And by examining that, maybe I'll deduce that. So let's go ahead and quit out of this and fix it. Right? Come back up here. What should it be instead? Int. If I was working with doubles, would that have worked at all? Nope. Doubles are 8 bytes. 8 bytes. All right. So let's go ahead and fix that to n. All right. Yeah, go ahead.
Why was it we were expecting 4? I thought it was 58.
Well, it will be. No, that's the sum, right?
Yeah.
So the output, yes, we're expecting 58, but we're getting 7 here, right? 7, not 4, right? So when I printed out size of int, I got 4 as expected. When I printed out size of n, I got 4, which is also expected, but just because they're both 4 doesn't mean it's right. All right. So GDB again, all right, and layout source so that we can see it. You can also set breakpoints at particular functions. Right? So what I'm going to do is I'm going to set a breakpoint at line 17, though. Okay. All right. So let's go ahead and run it. It pauses at line 17, and it sets the first one equal to 2. Okay. Did it work? Well, let's print it out. Print primes sub 0. Yeah, it set it equal to 2. Before I execute this next line, what is primes sub 1? That's 0 because we haven't set it to 3 yet. But if I go next, now it's set to 3. Let's print it to see if it worked. Primes 1. Yep, it worked. Okay. So I have a pretty good confidence here that all the values were set. I don't want to have to go through and print out each one. So you can print the contents of an entire array if you want. Print. It's an array, so it's a pointer, so I'll dereference it. Primes. And I'll tell you how many that I want you to print. At 7, because there are 7 things in that array. 2, 3, 5, 7, 11, 13, and 17. Did they all get set correctly? Looks like it to me. Right? So my problem's not there. Now, if I were to hit n right now next, it would actually skip over that function call. There's a different command to go inside of a function. So let's run this from the beginning again. Run, yes. Right. And what I'm going to do is I want to set a breakpoint. I can go next, 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 next. I don't like that. All right. Now, before going to next, I'm going to step into that function by using step instead of next. That takes me down to the function. Okay? Now, what is the value of I now? Undefined. Why? Because we haven't started our for loop yet. What is the value of total? Oh. So that should look familiar to some folks, that especially if you've been using Windows or something, right? What value does total have as of line 32? Undefined. Their definition is 32,767, right? So I found another bug. What did I forget to do on line 32? Initialize it to 7, right? Let's go ahead. So mark that down in your head, and we're going to fix that, right? Now let's go through the entire loop, right? So next. Okay, print total. Well, that's going to be 32,767 plus 2, right? So garbage plus 2 is still garbage. Next. All right, garbage print total. Garbage plus 3 is still going to be garbage. But you see that it's adding 3, right? Didn't it add 3? Yeah, it did. Okay. So I think that the loop is correct. So let's go ahead and fix that bug now. Quit. Yes. All right. And let's go down here and let's initialize our value here to 0. Okay. So now recompile it. Unfortunately, you have to redo this every single time. There is something called a hot fix that's supported by some compilers. I'm not sure if GDB supports this or not, but you can go back to the source file, change something, recompile it, and it'll, without having to close the debugger. Maybe it doesn't support it, but some debuggers do support that. Dynamic changes, basically. All right, so let's bring this back up and layout source. Also, all of your breakpoints are reset every time you quit and you come back in. So I don't have any breakpoints right now. I don't want to have to jump down, break at line 16 and then go next. I want to go ahead and jump immediately to sum. So you can actually break sum. Instead of a line number, you can provide a function name. Right? And if you can scroll up and down with your arrow keys, by the way, and you'll see here that the breakpoint has been set at the beginning of the sum function. Now let's run this. Okay. All right. Now we're in there. Next, print total. Okay, it's 0. Next, print total. Oh, now it's 2. Next, it should be 5 because 2 plus 5. I don't want to have to type this every single time. So I can set a watch on total. Right? What that'll do is it'll every time that total changes, it'll tell me without me having to print it out manually. So next. The old value is 2. The new value is 3. Right? And it occurred on line 33. Now you're at 33 in some line 33. Next. What's the next prime? 5. 5 plus 5. So it becomes 10. The next prime after that is 7. So it should go to 17. Looks pretty good so far. 28. 41. 58. We got our answer, right? That was the 58 that was reported by Wolfram Alpha here, right? Next. Print S. What happened? The function correctly computed 58, but for some reason, when it returned from the function, it gave us 7 instead. Something's going on like that, yes. Yeah, let's quit. And let's always remember to use not the suppress all warnings flag, but let's turn on all of the warnings now. What is it telling me? Control reaches the end of a non-void function. In other words, it returns something, but you do not have a return statement here. Bingo. What should I be returning? Total. All right, GCC this. Run it again. In fact, sometimes I just run it to see if everything's fixed without having to go through GDB there. 58. All good? Works on my machine. Ship it. What else should I do, though? Val grind it. Why? Because it might come up with errors that are still errors that are not manifesting themselves somehow. Right? This one though is not a worry. The error is a memory leak, but we're in the main, so I don't care about that. Yeah.
What's the difference between a bug and an error again?
Good question. A bug is a bug is more specific, you could say. An error could be anything that's not a bug too, like somebody kicked out my power cord, right? That we got bad data from the user. That's an error, but it's not a bug because I wrote my program correctly. You didn't enter data correctly or something. So an error is more of a catch-all term. A bug is something that is wrong with your program. Right? Yeah. I mean, it was, so the folklore is that one of the first computers, the vacuum tube wasn't working. It was because a moth was stuck in it. There was a bug in the computer, a literal bug. But I think that the truth is that term goes back even further than that, before vacuum tube computers even. So who knows where it came from, but the story is it's a literal bug in the program. Right? There's a moth in there impeding the vacuum tubes from working. Right? All right, so there we go. I think that's it. Again, the only other bad thing about this program is that we have a memory leak. If you wanted to fix that up, you could, of course, free primes, GCC this again, and run it through Valgrind again, and you'll get a 100% clean bill of health here. No problems here whatsoever. Okay. So now let's come back over here and review the commands that I just went through. So to get started, once again, gdb a.out. I should have just gone /a.out. Right. To display your source code, use layout src. If you really want to, and in fact some of you will be taking systems courses later on, where you'll use GDB to actually look at the machine code and to look at the assembly code and to debug assembly code. You can look at the assembly itself. Right? Sometimes the display glitches. Right? If that happens, just type refresh, and it'll redisplay everything. Right? We didn't have any problems, so I never had to type refresh. Right? To restart a program, use run. Right? Pretty straightforward. You can set breakpoints. Right? Breakpoints are pauses in the program, right? By line number. So you can, for example, you can say break at line 14. Right? So this is line 14. You can break at a function. Right? So break at sum is what we did. You can break in a line in another file. You can go break whatever your file name is, .c, and then a colon, and then the line number. So this will break at line 12 in the file.c. Right? So when you've got in your projects now, you're going to have your hacks and your labs. You're going to have multiple files going forward as default. And so if you need to set it in not in the main file, but in some other library file, then you'll have to use this syntax here. Right? We talked about how to add a breakpoint, but we never talked about how to remove a breakpoint. Remove a breakpoint. What was it? Oh yeah, clear. Right, this clears all breakpoints. Otherwise, if you want to clear that breakpoint that you left at line 14, you can go clear 14. Right? Clears the breakpoint at line 14. Basically, whatever you use to create the breakpoint, you clear, and then the same command there. Right? You can go to the next line, next executable line of code using next or N for short. Because it's such a common operation, you can use abbreviation. In fact, all the commands you can use abbreviations if it's not ambiguous. Right? You can step into a function using step. Right? If you don't, then it'll immediately step over that function. Right? Otherwise, the function is skipped. Function line is skipped. Right? All right. If execution is paused because you went at a breakpoint, you can continue it using the continue command, right? And that just means that it'll continue going there, right? Let's see. You can print variable values, right? So you can say print I or print n, whatever the variable value is. You can print entire arrays, right? And so if I've got an array called ARR, I need to dereference it, then I give the name, and then I give an @ sign, and I tell it how big it is. Say 7, or if it's stored in a variable, you can go with a variable name instead. And that's a better way of doing it anyway. But if you only wanted to print the first 3 or something like that, you could put a 3 in there and it'll only print the first 3. Right? So you can print entire arrays, just make sure that you're dereferencing them and using that @ symbol there. Right? Watches. You can watch a variable, and when its values change, it is reported. And you just go say watch I or whatever your variable is, right? Oh yeah, that's right. If you are trying to debug an infinite loop, now you have a nice tool to do this, right? Run GDB and then use control C. It doesn't kill it. It pauses it. Right? So you're stuck in an infinite loop and you don't know why, right? Because you're in this in this infinite loop, right? In fact, let me do it. For int I equals 0, I is less than 10, I minus minus. There we go. Printf I is equal to hello, whatever. Right. Let's go ahead and run that now on GDB. And let's hope that it doesn't crash immediately. There we go. And layout source, because I do want to see it. Now I'll hit run here, and it's going to get stuck in an infinite loop printing out hello, 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 hello. If I go control C, then I can start taking a look around. Refresh it because it is screwed up here. Layout source. Oh, come on. Refresh. It wasn't control C. Oh, I did command C. Let's run this again. Yes. Control C. No, come on. You should be able to show me. Refresh. Next. 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 Oh, that's why. When I killed it, I was in the system level stuff. So let's go ahead and go next there. Next. 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 Until I get back to my code here. You see all this stuff? This is like system, lower level system stuff that I don't have access to. There we go. Now I'm back to my program, right? So it was an infinite loop, and it was infinite even at a lower level here, right? And now refresh it. There we go. Now it's all cleaned up. Okay, what's going on here? Now we can start taking a look around. Next, next. It just printed hello. Next, next. It just printed hello. Well, I now at this point is negative 100,000 or something, right? And why? Because I was just going minus minus. You see here it screws up. Refresh. Just refresh will repaint the screen here. Right? Watch. I. Next. Next. Oh, it's going down. I see what the problem is. It's going from refresh. It's going from, you know, okay, I've got that wrong. I'll fix that. So exit or quit. There we go. And let's get rid of that infinite loop there, right? By just commenting it out. Right? So you can pause it. So I'll put an addendum here. Careful, it could pause in lower level machine code, right? Machine or library code. So you just need to just keep hitting next until you get back to your code. Right? All right. Some other tips and tricks here. Command line arguments, you can use those as well. Right? So command line arguments, you can invoke your program through GDB so that there's a way to, you invoke it through GDB so there's no way to set command line arguments, but you can go ahead and set them manually when you're in GDB. Let me show you really quick here. Let's go ahead and GCC this so that that infinite loop is gone, right? And at this point, argv and argc are not set, but you can set them by using set args here, right? Paste. There we go. Now I can print argv sub 0, which is a dot out. Oops. Okay. Layout source. It's not running, that's why it's not printing. And let's go ahead and break at main and then run it. All right, now print argc here. 5. Why? Because what did I set it to? A, B, 10, and 20, but that first one is a dot out. So print argv sub 1 or 0. There's that a dot out. Print argv sub 1. There's that a. Print argv sub 2. There's b. Print argv sub. Oh, I just did it. Print argv sub 3. There we go. And there's that 10. Okay. You can even invoke C code. For example, I would say, what happens if I converted that second command line argument over to an integer? So print a to I of argv sub 1. Remember that's a, so it'll be 0. Print a to I of argv sub 3. Remember that's 10, so it'll end up with a value of 10. This is called a REPL, R-E-P-L. What is it? Repeat, evaluate, something process or something. I forget what REPL stands for, but it's basically a code environment where you don't have to write a full program. You can actually execute individual single commands in the language, and it'll show you what would happen if you executed that in an actual program. What does REPL stand for? Re-evaluate or read? There we go. Read, eval, print, loop. There we go. Thank you. All right. So you can set command line arguments. Like I just said, you can actually do basic commands in GDB, printing something. You can multiply things together and see what the results are. You can look at the entire stack trace by using backtrace full. So that's useful if you ever have a seg fault. How did I get to this point? Yeah, I know the seg fault happened on line 13, but who called the function on line 13? You can read an entire backtrace here, backtrace full, and it'll give you a lot of information if you've got enough real estate here. Right? All right, there's n, there's the primes, there's s, right? And you're at line 13 here. You only have a main, but if you set a break in sum, and I will continue. There we go. Now let's go ahead and look at the backtrace full. You'll see that main called sum, and here are all of the values associated with it. It's like basically a super print everything. I want to look at everything. And it's a backtrace full. All right. Okay. Really cool thing here. You can set conditional breakpoints. Right? So for example, let's go ahead and come over here and let's get rid of this now. Yeah. And let's come back to my program. And suppose I have this for loop, but I fix it, right? And I'll print out an integer here that is going to be, I don't know, let's go up to 1 million. Right? And I will say 1 divided by, or no. What do I want to do? 1 divided by 500,000 minus I. And I will do this as a double. Right? There we go. Now, predict what's going to happen here. Is there a value of I that this is going to screw up on? Yeah, what? Oh, when the denominator is 0. When is the denominator 0 here, though? At 500,000, right? Because 500,000 minus I is 500,000 gives me 0, right? This is 500,000, right? Yeah. All right. So, obviously this is a made-up bug, so we can see that immediately. Oops. Exit. GCC, then GDB, And if I were to run this, a.out, or run, right, it's not going to occur until x is 500,000, right? Okay, we might get there eventually, right? I'm going to go ahead and get rid of this print statement entirely and just have a double x is equal to. Eventually, this is going to lead to a division by 0, right? So exit, quit, right? Yeah, GCC this. Yeah, it's warning me too. Unused variable. Oh, there's an error. Sorry. What's the error? Oh, too many parentheses now. There we go. GCC this. GDB. Now I'm going to set a breakpoint at break main layout source. All right. Now run. All right. Everything is cool up until this point. Refresh. All right. Now, to actually reproduce that bug, I'm going to have to go next. How many times? 500,000 to get to the point where the bug is manifest. Yeah, better get going. Or I can say break at line 32 if I is equal to 500,000. Right? That's the correct syntax. Yeah, there we go. Right. Okay, continue. Right. Continuing. I don't know why it's taking that long, but whatever. That's okay. So everything is going to take way longer because this is, of course, a program running another program. So you have a bunch more overhead there. I shouldn't have done 500,000. That's way too much. All right, quit. Let's do 150. CCC, GDB. All right. Now break at line, what was it? 31, if I is equal to 50. All right, layout source and run. Refresh. All right, print I. You see that I is 50. Okay, well then what is 50 minus I? Okay, it's 0. So therefore, what is 1.0 divided by 50 minus I? Inf, not a number, whatever, right? So you can set conditional breakpoints using that syntax. And you can put any valid C expression that you want. X is equal to 23. If X is equal to 23 and Y is less than 0, right? Stuff like that. Right? Again, you must recompile for every change and then fire up, quit out of GDB, recompile, and go back into GDB if you need to, because there are no hot fixes. But some compilers do support that. Right? There's a lot more that you can do with GDB. This is only the tip of the iceberg. But from now on, especially after next week when you use GDB to debug this tic-tac-toe program that we give you, the first thing that you should do is, oh, it doesn't work. Well, what are you going to do? Fire up GDB. Find out where it doesn't work. And then set a breakpoint and jump to that location and take a look around. What are the variable values at this point? Oh, I've gone, my array is of size 10, but my index variable is 20 for some reason, right? You know immediately that something happened there. Run valgrind to see, do I get a complete clean bill of health on my entire program, right? Or do I need to go back and fix things, right? This is how you diagnose any errors like that. All right. So on Friday, we'll go over some more tooling. Actually, it's more of a review of looking at the tools that we've looked at so far. I'll mention a few more because GDB and valgrind aren't the only tools that you can use to diagnose things. GCC itself, we know that can be used as a linter. I'll show you some other things that you can do to diagnose problems, because now we're getting to a point where your programs are going to be more complex enough that you can't just use print statements to find out what's wrong with it. You can't just stare at a screen and say, okay, there's the problem, right? Unless you're really, really good. In fact, there are advocates, mostly wrong advocates, that say that you should not ever use a debugger. The reasoning for this is, if you weren't smart enough to write correct code the first time, then you're not smart enough to figure out the bug. And they're absolutely wrong. Okay, that's absolute BS. Don't listen to any stuff like that. Everybody makes mistakes. Everybody makes small stupid mistakes. One of the most famous ones, most recently, is the go-to fail bug that was in iOS security checks. Right there, somebody fat-fingered a copy pasta there. They had two go-to fail lines here. It's clearly wrong if you just look at it. Oh, there are two of them there. Basically, what that does is it short circuits out this last check here to see if their identity was correct. All right, and this was in Mac OS systems for 20 years or something like that. And nobody ever noticed it. It was exploitable. People may have been exploiting it. And of course, if you're exploiting it, you don't want to, oh yeah, there's a bug over there, right? You want to be the black hat. You want to be the bad guy that can exploit something like that. But really smart people still made a stupid little bug like this of repeating something. Other bugs that have happened are like failing to think about a semicolon somewhere, or a colon, and it compiles and it runs, but it doesn't give you the results, and it doesn't manifest itself because you never see it unless you run it through something like this, right? So yes, you are all smart enough to figure out your own mistakes, right? All you need is the proper tools to do so, like a debugger like this, right? Those kind of people, I forget who it was. I think it was Linus Torvalds, who was an a-hole anyway in general, but having attitudes like that, no, you shouldn't be programming, right? Or something, those elitist gatekeeper attitudes, that's absolutely wrong. Don't ever listen to that crap, right? All right, so we will see you on Friday where we will talk about more tooling.